I'm Sarah and I'm going to talk to you about the implementation of dipole fields in the Vampire software package. So, what are dipole fields? Dipole fields, also known as demagnetizing fields, act to demagnetize the material. So the dipole field interaction occurs from every atom to every other atom in the system, just like the exchange fields. So we add the dipole fields in, just like we do all of the other fields. So we calculate the dipole field Hamiltonian, and then this is just added to the normal spin Hamiltonian. So now we've got the spin Hamiltonian equals the Hamiltonian due to the exchange, plus the Hamiltonian due to the anisotropy, plus the Hamiltonian due to the applied field, plus the dipole field Hamiltonian. So how do we calculate the dipole field Hamiltonian? So if we calculate the dipole field, this is a vector, and the dipole field equals the demagnetizing tensor dot the magnetization vector. So the dipole fields are calculated from every atom I to every other atom in the system, atom J. So the demagnetizing field equals N, which is a tensor, which represents the interaction between atom I and J, dot producted with the magnetization I. So what is the demagnetizing tensor? So I've shown the demagnetizing tensor here, and as you can see, it's proportional to the magnetization of atom J and the distance between atoms I and J. So as we can see here, it falls off with 1 over r cubed. So this can be split into two terms. The first term is the term due to all the other dipoles. So if you take one dipole, it's the interaction of this one dipole with every other atom in the system. And then the next is the self-interaction term. So this is the demagnetizing field that one atom feels due to its own magnetic field. So what are the problems with this? The main problem is that the dipole fields die off proportional to 1 over r cubed. Now, if you think of, say, the exchange fields, they are also the interaction of every atom with every other atom in the system. However, they die off exponentially. So this means that once you get to sort of a couple of nanometers away from the atom, you can basically just cut it off. So you cut off anything except for like either nearest neighbours or next nearest neighbours, usually with the exchange Hamiltonian. However, dipole fields are proportional to 1 over r cubed. So this means that instead of dying off, actually the atoms that are far away are still very significant. They're even more significant because at this point the exchange interaction has completely died off, so the dipole fields are way stronger than the exchange interaction at these points. This means that the calculation of dipole fields are very computationally expensive because you have to calculate the interaction of every atom in the system with every other atom in the system. So, how do we calculate the dipole fields? So in Vampire we have 3 methods which are already implemented and 2 methods which are very nearly implemented. So the first is the atomistic calculation. This is the interaction of every atom this is calculating the interaction of every atom with every other atom in the system. This is like very, very, very accurate, but also very slow because it's an n squared calculation. The next is the macrocell approach, which is quite a lot like the micromagnetic approach. So this is much faster, but a lot less accurate. The next is a tensor approach, which is faster than the macrocell approach, faster than the atomistic approach, and more accurate than the macrocell approach. The next is they're the 3 that are currently implemented in Vampire. The hierarchical will be released in the next version of Vampire, and it's even faster than the tensor approach, and again more accurate than the macrocell approach, and almost basically the same amount of accuracy as the tensor approach. So the next is the FFT, which should also be released with the hierarchical version. So this should be faster than the macrocell approach, but it is as accurate as the macrocell approach. So the first one was the atomistic calculation. So this is calculated between every atom in the system. So it scales as n squared. So it's the interaction of one atom with every other atom in our system. So this is really, really, really slow. It's impossible for systems larger than a couple of nanometers. However, it is really, really accurate. So this means that if you ever want to do something such as a domain wall or an antiferromagnet, these are basically impossible with any of the other methods, unless you have a really wide domain wall width. Then you have to use the atomistic. So the next is the bare macrocell approach, which is sort of the same as micromagnetics. So if you think of going from an atomistic to a micromagnetic model, this is what we've done here. We've summed up all of the atoms in a small area into cells, calculated the average magnetization of that cell, and given the cell a magnetization. So this is much faster than the atomistic approach. However, it is quite a lot less accurate depending on the cell size. Another problem is that the system is supposed to have a uniform magnetization. So this means that you can't really calculate things like antiferromagnets or ferrimagnets or domain walls. So problems with this is that often the magnetization inside a block is not fully aligned. It also still scales with n squared. So n is now the number of macrocells and not the number of atoms. So this means that it is way faster than the atomistic approach, but it still scales very badly with large numbers of cells. So next what we did is we created the tensor approach, also known as the inter-intra-dipole approach. So the tensor approach, what you do is you give each atom a cutoff radius. So here we have a cutoff radius of about 1.5 macrocells. And what you do is you calculate atomistically the dipole tensor for all the atoms within this cutoff radius. And then if it's further away than this cutoff radius, you use the bare macrocell approach. So this is way more accurate because if you remember, the dipole fields still do die off with 1/r cubed. So this means that the atoms that are near the atom that you're calculating are way more important than the atoms that are far away. But the atoms that are far away are still important because the dipole fields haven't completely died off, but they are a lot less important than the atoms that are nearby. So you calculate the atoms nearby atomistically and the atoms that are further away using the bare macrocell approach. So this approach is good because it works independently of the shape of the macrocell. After about 2 macrocells, you can use the bare macrocell method. However, as we've said before, it does require parallel moments, as with the bare macrocell approach. So this means that the cell size should be less than any domain wall widths. So now what we want to do is we want to test this theory. So we want to test the dipole fields and see if they work. So what we're going to do is we're going to create a thin ferromagnetic film. So we have a thin ferromagnet, so it's very thin, 1 nanometer in Z and 20 nanometers in X and Y. So the X and Y coordinates are much larger than the Z coordinates. So what I want you to do is I want you to think about what the magnetization should look like once it's equilibrated. So I used permalloy as my ferromagnet, and all the properties of permalloy are written on this slide here. So we're going to take our thin film of permalloy and we're going to run a time series simulation with a random initial spin direction, and we're going to see what happens to the magnetization. Okay, so this shows our permalloy material file. So it has all of the properties which we showed here. This is 3 μb, not 30 μb, as it said on the slide. And so they're an alloy of each other. So we've used this alloy specific property. So we've said material 1 is the alloy host. So that means that the whole system is initially created as nickel. And then you say the alloy fraction, so is 0.2. So that's replacing 20% of the nickel with iron. So then we should get a random nickel-iron structure. So we've set the exchange interaction as 3.78 and the exchange interaction from material 1 to material 2 and material 2 to material 1, so it's all ferromagnetic. Okay, and this is our input file. We've also set the initial spin direction to random. So this is our input file. So we want to change these. We want this to be 20 by 20 by 1. And then what we want, 20 by 20 by 1. We've said our material file is py.mat. So we've set our dipole solver to be the tensor solver. And we've set a dipole cutoff radius of 2. So this is 2 unit cell sizes, and we've set our unit cell size to be 1 nanometer. So now what we're going to do is we're going to run this using Vampire. So if we... Okay, so it's running. And as you can see, it started out being not very magnetized because we started it in random configuration. And for every time step, the magnetization length is growing. Okay, so our simulation has now finished. And as we can see from our output, the magnetization has aligned along the X direction with a very, very, very small out of plane component in the Z direction. So it's basically completely in plane. This is what we'd expect because the minimum energy occurs when all the atoms line in plane because this minimizes the demagnetizing fields. So what happens if we run this same simulation but we get rid of the dipole solver? So I've just commented it out, and then we're going to run exactly the same thing again. So now our simulation has finished running, and as you can see, the magnetization is still along X. However, this time there is a much, much larger Z component, and this is because without the dipole fields, there is nothing to push the magnetization into the plane. So now what we want to do is we want to create a different type of shape. We want to create a cylinder with a large component along Z. So we want to create a cylinder. So again, we're going to use exactly the same material. We're going to use permalloy, but now instead of a plane, we're going to run an elongated sphere. What should happen to the magnetization? So I want you to stop and think about this for a little moment, and just think about what you think will happen to the magnetization throughout this simulation. So we've set our system sizes to 2, 2, and 8 nanometers, and then we've created a cylinder with a particle size of 4. So 4 is the diameter, and a particle shape factor of 0.5 by 0.5 by 2. So our particle size is 4. In X, that's 0.5, so that's 2. In Y, that's 0.5, so that's 2 again. And in Z, it's times 2, so it's 8. So that should create a nice cylinder that's elongated along Z. So now we want to add in the dipole fields. So what we want to do is we want to include the cell size from the macrocell. So we're going to use exactly the same cell size again. We're just going to use 1 nanometers. And then we're going to choose our dipole parameters. So we'll just keep those exactly the same as the past simulation. And then we'll choose whether we want the tensor cell or the tensor or the macrocell approach. So if we start with tensor again, just like we did before. Okay, so we want to change our particle sizes. So X was 2, Y was 2, and Z was 8. And then include all of these cylinder terms that I commented out before, and everything else stays exactly the same. So again, we're going to run a time series calculation and include the tensor calculation again. And then the material file just stays exactly the same. So now we're going to rerun this simulation and see what happens. So now our simulation has finished running. We can see that this time the magnetization has a strong out of plane component. So it's strongly along Z. Okay, so the next thing that we want to do is we want to compare the different dipole field solvers. So as I told you, there's already 3 dipole field solvers implemented in Vampire: the Atomistic, the macrocell, and the tensor field. So what I want you to do is I want you to compare the 3 different types of solver and see things like speed and output magnetization. What you should find is that the atomistic solver is much slower than the other two solvers, but they should all give relatively similar results, with the magnetization ending up along the Z direction and in plane for the thin film that we modelled before. Okay, so now I'm just going to briefly go through the other two implementations that will be released in the next release of Vampire. So the next one is called the hierarchical model, and it's very, very, very similar to the tensor model in that it has the same sort of, if the atom is near it, you model it using an atomistic approach, and as the system, as you move away from the atom, you break the system up into macrocells. However, as you break the system up into macrocells, as you get further and further away, these macrocells get bigger and bigger. So this is just shown in this diagram here. As you can see, when you're near the red dot, so the red dot is the one that we're modelling, that you model everything atomistically. And then as you get further away, you use small cells, and then you use bigger and bigger cells as you get further and further away from the initial red dot. So how does this scale? So the scaling is shown in this graph here, and as you can see for the tensor, the calculation time increases with an n squared plus n plus c scaling. So it's basically an n squared scaling, which is really, really, really slow because it increases with the number of macrocells. However, if we drastically decrease the number of macrocells, we should get much better scaling. The hierarchical scaling is also shown on this graph, and as you can see, is orders of magnitude faster than the tensor scaling. So this was for a really big system. Obviously for small systems it makes very little difference, but when you're looking at things that are like hundreds of nanometers big, it makes a very, very big difference. So the other calculation that we're looking at implementing is the FFT calculation. So this assumes that the crystal structure is spatially invariant. This is true because we split the system into cubic cells, so all of our systems should be spatially invariant. And then we calculate a Fourier transform. So instead of doing h equals n dot m, we instead calculate the Fourier transform of h, which is the Fourier transform of n times the Fourier transform of m. And then we inverse this, so the Fourier transform of the Fourier transform of m times the Fourier transform of n. So the Fourier transform of n only needs to be calculated once, because this is always the same, and then that just needs to be multiplied by the magnetization at every time step. So this is the predicted speed increase compared to the macrocell. The macrocell should scale with n squared, and the FFT should scale with n log n, so it should be much, much, much faster. Okay, so this has just been a short introduction to how to use the dipole fields in the Vampire software package. Thank you for listening.